exactly.
हो गया?
एक्स्ट्रा पासवर्ड के लिए चाहिए अटेंडेंस ऑन करनी ना
ये अटेंडेंस वो फ्री कर देंगे आप लोग देने को
ओके
क्या what's going on
मैं नाम लिखने लगा
तो और क्या लिखेंगे आप you have some other identification
मेरा पेन नहीं है
तो पेन इसके आपके जो साथ बैठे उसके पास भी नहीं है
उसने नोट्स लिख दिए
तुम दे दें So last time we established that how to write the Hamiltonian in the presence of electric and magnetic fields. When electric and magnetic fields are present, you have dealt with such quantum systems in some cases, basically in quantum mechanics 2 when you were doing perturbation theory and you saw that applying fields, how can you, for example, cause transition in atoms or split the atomic levels. In this course, I'll try to use as little perturbation theory as possible. Probably we will not touch it at all, or we may have to use it at some point. Then we will kind of quickly review it. But I'm going to do one example today, which is one quantum dynamics when you have a particular kind of field applied. So this is just a review from the last time. We established that the Hamiltonian is this. You have to write it in terms of the potentials. Can't do it directly in terms of electric and magnetic fields. And where this P is this ordinary momentum, ordinary mechanical momentum is usually people just don't call it momentum. The canonical momenta is what we call momentum. It's related to the coordinates and the field in this way. So the physical momentum, the mechanical momentum, if you just take the speed and multiply it by the mass, what you usually call the momentum, that's not called canonical momentum, but it's useful if you want to ask what's the speed of a particle, is the thing which you look at it. So let's give it a name, let's call it pi. So from here is just P minus P over C. Okay. Okay. That is the physical momentum. Now let's discuss an example, and the example is this. You have a magnetic field, you have a slab, a thin slab like this, or let's say some metal. So there are 3 electrons available in this material, maybe some semiconductor, and you have applied a constant magnetic field. In the z direction. So the slab की directions हैं इसको मैंने x and y कह दिया और magnetic field is applied perpendicular to the slab. So if you recall from some of your previous classes, this is the setup for Hall system. Now if I apply a voltage across over here, then this is what you are told in a hand waving wave. Okay, electrons are trying to move this way but you have a perpendicular magnetic field, so they feel a drift in this direction, and you measure a Hall voltage across this direction. Okay, this is X, this is Y. You apply electric field along X, you feel a Hall voltage along Y because electrons are feeling a force over there. You feel like you measure a current across this direction, across this cross section. So this is all known, and we're just going to derive this in a more careful way, just to see this formalism in action. And first I'm going to just do it classically, just to get a feeling what's happening over here. So if I'm going to apply this Hamiltonian system, then I must use the potentials. So I have to guess, as I said, that you always have to guess a function, so that you have to guess an A, so that del cross A gives you your desired field. So an easy guess is this one. I can take this to be my vector potential. These are my components. X component depends on Y, it increases with Y. And Y component of this potential depends on X, changes with X, and there is no Z component.
So this one has guess necessarily as well, because if I remember correctly, this is like a detailed spatial sort of an integration that you can carry out using the sources for the vector potential.
Why would you make your life hell using that? I mean, doing that integration is very hard. And in the end, what you are after is some vector potential which gives you the field. And we know that it's not a unique, there's a huge choice. The gauge freedom is there. So it's just one of the guesses. You can check it. तो क्या है, माइनस y इधर है, x इधर है, 0 इधर है. This gives you 0. I component, j component is again 0. Only the k component gives you 1 and plus 1. So in the end I want this strength, B0. So I can multiply this whole thing by B0 over 2. Because I get over 2 into 1 plus 1. So this is a good enough potential. And now I can write my Hamiltonian. So what you need to do, shift the momenta by the potentials. So Px minus this guy, but this gives me plus Pb0 over 2c y square plus Pb0 over 2c x squared. So this is the Hamiltonian. And now I can find the Hamilton's equations. Ex dot is, let's first write the x equations. X dot was just d8 over dx. तो यहाँ से क्या आ रहा है? 1 over 2m. Px is only over here. me y dot लूंगा तो उसमें I'm just differentiating with respect to this guy. It's going to give me 1 over m py minus ev naught x over 2c. Hamilton's equations start में first order होती हैं, so I have the derivative of px dot अब इसमें only this guy is depending on x, explicit x dependence है, so I get 2m and I have minus from the formula and the 2 from there. Py minus ev naught over 2c x, and then differentiating with respect to x. This यही जब मैं पी वाई के लिए करूंगा सारे नेगेटिव साइंस वही हैं except I don't pick up this negative sign from here, so there's a difference of a overall negative. Yeah. And px plus ev naught over 2cx. And in the end, I just want to, so these are the complete set of equations. If I want to solve it for the coordinate x and y, then I have to like kind of eliminate px over here. px यहाँ पे डाल के इसको solve कर लूँगा, मगर बस px नहीं है, px dot है. So what you almost always end up doing is get a second order equation for x, which is just your Newton's second law. So if I take derivative of this equation, time derivative, I get x double dot is equal to 1 over m and dx dot plus ev naught over 2cm y dot. अब px dot जो है इसकी वैल्यू मेरे पास ये है, so I can replace it over here, and y dot is also present, so this gives me ev naught over 2c m square, एक m यहाँ से आ गया, बाकी सारा मैं सिर्फ p y dot px dot के एक्सप्रेशन प्लेस कर रहा हूँ, cx y dot की अब ये डालता हूँ py minus ev naught over x. So they just add up to give me this guy is common, but this guy is, if you look back over here, py, if I pick the jth component, over here. It's py minus e over c, ay, and ay is x b naught over 2. Okay? So this is actually giving me the mechanical momentum. And I have a m square over here. So this whole thing is equal to m y dot. So this m I can cancel, and this y dot, instead I can write it as vx, vy. So this is my first equation. X double dot is equal to EB naught over MC, and maybe let me write it clearly over here. If you do it for the y dot, everything is very symmetric. Same thing is going to happen, except that वो जो एक minus का difference है, that you pick up over here. Vx. So these are basically coupled equations, first order coupled equations for Vx and Vy. दो variables हैं, Vx and Vy, because x double dot is just V dot. ठीक है? X double dot is like Vx dot. So इसको decouple करना बहुत ही easy होता है, अब तक तो आपको आ चुका होना चाहिए. Usually I do it in my class, but I'm not going to do it today because I want to make some progress. I'm just going to write the solution, which you can just quickly check. तो मैं सिर्फ इस इक्वेशन को दोबारा लिखा हूँ. y dot vx, where this guy, ये जो constant है, इसको मैंने सिर्फ name दे दिया. So the general solution is जनरल सॉल्यूशन में कितने कांस्टेंट होने चाहिए? 4, क्योंकि सेकंड ऑर्डर इक्वेशन है x और y. ठीक है? And the solution is that's fine.
When you said you were going to uncouple, then what you meant was that you can, for instance, difference.
Yeah, I can write it like this.
The first equation once.
इसको मैं v dot लिख लूँ, vx dot omega की, save some space. ये पहली इक्वेशन है ना, vy, ये दूसरी है, vx. अगर मैं इसका डॉट लूँ, I get v double dot x vy dot. Vy dot मेरे पास यहाँ पड़ा हुआ. So I will get v double dot x in terms of vx, which is very easy to solve.
Yeah.
Which will give me this as a solution.
And the x naught and the y naught, they are very constants that you pick up when you
When you integrate the vx, exactly. So आपके पास जो solution vx और vy का आएगा वो ये होगा. And then you integrate once more, you pick up another solution. This you can just put and check. These solve it. Double derivative है, ये तो double integral differentiation में दोनों तो खत्म हो जाते हैं, and the rest is solved. So what is it giving you? ये किस किस्म की मोशन है? अभी सिर्फ मैंने मैग्नेटिक फील्ड अप्लाई की हुई है, कोई इलेक्ट्रिक फील्ड नहीं. This is giving me kind of circular motion. If I square x square plus y square, I get a circle centered around x naught and y naught. इसका बदल लेते हैं. तो square जो है हमारा gives you this x minus x naught square plus y minus y naught square is r square. So what you have is that in this lab, the electrons are moving in circles because of application of magnetic field. What is the size of this circle? Huh?
So maximum R over
Maximum R होगा. ये solution क्या बता रहा है आपको? क्या size है?
radius R. Radius R.
R क्या है?
Is radius.
Radius तो है. उनके से क्या value होगी?
Oh. देखना पड़ेगा.
इसको देख के क्या नजर आ रहा है? इस equation में क्या है? What does this equation tell you? It's arbitrary. It was an arbitrary constant. You can choose it anything. So all these motions are possible. You can make circles. Electron could be going in circle of any arbitrary size. But it doesn't matter which circle it goes in. This circular motion has a frequency, omega. So all these circular motions have same frequency. It comes back, goes around the circle in same time. This is called the cyclotron frequency. And you can put this circle anywhere you like on this slab because there is translation invariance. Doesn't matter where you are on this field is uniform all along this slab. That's reflected in this. But since it makes bigger circle is completed in same time as the smaller circle. So the bigger circle over here, the particles have higher velocities. So they have more kinetic energy, more energy in this circle. There's no potential energy. The magnetic field doesn't give you potential energy. You have more energy in higher circles. So there are these two kind of freedoms available to you. Electrons could be having different motions. They can be having different energies. You can give it as much energy as you want. And you can place it anywhere you like. Now, what if I apply an electric field? In presence of electric field, this equation is changed. I'm not again going to go through the whole Hamiltonian procedure. Maybe you can do it as homework. But we know what it's going to do because this is just giving me the acceleration. This is acceleration. So I already know from Newton's, from Lorentz force, कि क्या होता है, how it's going to change. तो फील्ड मैंने इस डायरेक्शन में अप्लाई किया, x डायरेक्शन में यूनिफॉर्म फील्ड. आगे बस एक्स्ट्रा फोर्स, चार्ज इंटरैक्टिंग विद इलेक्ट्रिक फील्ड, बस ये आ गया. That's it. Equations actually हमें पहले ही बता दी. These are just force equal to acceleration equal to v e over c times v cross p. ये सब प्रोसीजर सिर्फ एक इंस्ट्रक्शन के लिए हुआ. तो इसका जो solution है, that again I'm just going to tell you. ये terms तो वैसे ही आ गई. So in this case, what happens is, physically this solution, what is this solution telling you? All it's telling you is कि ठीक है circles आपके पास हैं, मगर y जो है coordinate है is drifting. It's drifting with time. So this is not your actual motion. The motion is like this. So you have a current going on. फिर यहाँ apply किया, current ऊपर जा रहा है. जी.
So in the first case, circles आपके सारे concentric नहीं होंगे?
नहीं, concentric क्यों होंगे?
क्योंकि
यहाँ
आप
arbitrary.
x0 y0 arbitrary है.
Electrons could be doing anything.
Okay.
So technically they depend on the initial conditions, right?
Yeah,
exactly.
initial conditions of electrons. So they, in the material you will be having all kinds of initial conditions. So the current is in this direction. So you either apply the current either. Usually when you think of Hall current, you think कि शायद इधर भी जा रहा होगा जब field apply किया और reflect हो रहा होगा. But most of the electrons, at least those अगर ये material slab आपकी काफी बड़ी है, they will not be able to go in this direction. क्योंकि यहाँ कोई नहीं है, यहाँ जो motion इनकी है वो circular है. So they don't reach over here. Only certain orbits will be able to go from here to there. वो कौन से कोई बहुत बड़ा circle है. ऐसे जाने को जो कर रहा है, only that will be able to do that. So that's called the kind of the edge states. Edge को touch करके जा रही है. Most of the other states, the smaller cycles, and they don't move this way. They just move this way. So you have a high resistance in this direction, but conduction in this direction. So this is all about the classical picture. And now we're going to see what happens in quantum case. It's important from two perspectives. पहला तो ये कि it's your kind of first example of solving an Hamiltonian with an electric or magnetic field exactly. Probably you have done something else as well. But also we will be coming back to this system again and again during the course. So this is just the foundation of what a quantum Hall system is, because it has lots of very interesting properties, which we will explore as we go on. So now, what about the quantum problem? Maybe I need to draw it. This is small thing. So quantum problem में again Hamiltonian मेरे पास मौजूद है, कहाँ लिखा हुआ है? ये लिखा हुआ है. इसमें सिर्फ जो last time हमने prescription दी थी वो ये थी कि जो canonical momenta हैं, they become the momentum operators as you go to quantum mechanics. Square. So these are all x and y are now operators.
So there was this जो electric field है, the constant field that you have applied, that sort of that should have
The magnetic or electric?
the electric. So that shouldn't that have like there should be a phi associated with the scale.
Yeah.
So you're not quantizing.
No, now I will move the E. I'm just quantizing with the magnetic field. Magnetic field is here. So I'm just looking at the analogs of this cyclotron motion. There's no electric field. ये काफी लंबे constants हैं, so इसको using this I'm gonna just simplify it a little bit. Px hat plus m omega square. This is the same omega as over there, which incidentally in classical case is the cyclotron frequency.
Isn't there an extra two?
कहाँ से?
So,
E B naught over MC. वहाँ पे क्या है? E B naught.
do you multiply an m with it?
Yeah. There should be 2. Oh, it's not there in my notes. Maybe I missed it somewhere. Let's put it over here. Okay. I hope my rest of the notes are not screwed now.
So shouldn't it be in the denominator?
Huh?
Be in the denominator.
M omega over 2. So let's do one thing. यहाँ पे आप क्या कहाँ पे 2 एक्स्ट्रा आ रहा है? यहाँ 2 है ना? इसको हम 2 कह देते हैं. तो हमारी सब इक्वेशन में क्या आ जाएगा? ओमेगा 2 ओमेगा. ठीक है? So I just don't want to use my notes right now. ठीक है? So in the end, I'm gonna replace, when I'm talking about cyclotron frequency, I know cyclotron frequency is twice my omega. Because the frequency is this one. तो अब ये जो है, ये वैसे तो लग रहा है कि इस Hamiltonian, now the idea is to find the eigenstates of this Hamiltonian, and looks like it must be horribly hard, but it's not actually. Just stare at it carefully, you find that it's like a harmonic oscillator. There are two operators, एक ये operator और एक ये operator, इन दोनों का square होके ये दोनों add हो गए. This is what happens in harmonic oscillator, p square plus x square, दो operators हैं, square होके add हो गए. But you can solve it because p and x has a particular commutation relation. Turns out these operators have the similar commutation relation. So let's give these operators a name. Pi x hat. Pi x hat क्यों कह रहा हूँ? क्योंकि actually classically pi ये जो combination है is just the mechanical momentum. So this operator is the operator for the mechanical momentum. Classical limit में अगर आप जाएंगे, this guy will give you the moment and the speeds. But in any case, you don't care, whatever it is. Go ahead. Set. And now let's check their commutator. वैसे तो we know that momentas commute, but the canonical momentas commute. These mechanical momentas, it turns out that they don't commute, and you can just wipe out the commutator. Exact. तो इसका और इसका commutator 0, इसका और इसका भी 0 because x और y का 0 है. इसका और इसका gives you minus m omega p Px hat x hat. और इसका और इसका gives you m omega y hat e hat. Since they are canonical, so this is IH bar and these are also canonical, so this is minus IH bar. So you get this equal to iota 2m omega h bar.
You want to rescale the operator so that you get average?
I don't want to. I can, but so they are like position and momentum. Px is like position and Py is like momentum. Because position and momentum have commutator equal to I times a constant. That constant has saying it's not h bar, it depends on what is the field. If you put field equal to 0, this will become 0. Because in that case, you're back to the ordinary situation where mechanical momenta are the canonical momenta and they have to commute. But if this is so, that means I can solve it. The Hamiltonian is just harmonic oscillator. So how would you solve it? It's now just a review. So what you do in case of harmonic oscillator. So let me define the creation and annihilation operators. Creation and annihilation में you x plus iota p x, that's what you do, right? तो यहाँ पे this is like position, this is like moment. और ये जो आगे coefficients हैं, that you have to adjust so that you get a dagger commutator equal to 1. This you can easily check. ये जब मैं कम्यूटेटर लूंगा, दोनों के साथ ये है, बाहर ये आएगा, ये टर्म्स तो 0 होंगी, cos टर्म्स जो है, like pi x pi y, that gives me एक पे बस माइनस iota यहाँ से है, and pi x pi y gives me iota 2 m omega h bar और यही चीज मेरे पास इस कम्यूटेटर से है, ठीक है? तो 2 टाइम्स ये हो जाएगा, iota माइनस और इस माइनस से कैंसिल हो गया, this times 2, this whole thing cancels with this, and we get equal to 1. Hamiltonian in terms of these guys just becomes h bar omega a negative a plus r. If you don't recall this calculation, maybe I think it's just the third class, maybe you can go over quickly. px स्क्वायर क्या देगा? यहाँ से if I add them I get px. So px is ये अंडर रूट 2 देगा, the 2 है, ये ऐड करके इससे अंडर रूट 2 आ जाएगा, दोनों साइड पे कैंसिल हो जाएगा. So I just get under root n omega is bar and p hat y. Now I'm subtracting. Subtract किया तो I get an iota over here. जिस साइड लेके जाऊंगा तो माइनस iota हो जाएगा. And px square plus py square m omega h bar कॉमन हो गया. इसके स्क्वायर से मेरे पास ऐसी टर्म्स आ रही हैं a स्क्वायर प्लस a dagger स्क्वायर प्लस a hat a dagger प्लस a dagger a hat. इसके स्क्वायर से आ रही है आयोटा का स्क्वायर माइनस dagger स्क्वायर. यहाँ से क्या आ रही है? आयोटा का स्क्वायर माइनस है, यहाँ पे माइनस है तो अगेन आई गेट अ प्लस a hat a dagger plus a hat dagger a. So you have 2 times m omega h bar a dagger a plus a hat a dagger. एज में मैं इसको डालूंगा 2m कैंसिल हो जाएगा. एज बार ओमेगा and when you flip it, इसको flip करेंगे आपके पास आ जाएगा +1. so ये दोनों ऐड हो गए. Something went wrong. I'm missing the 2. 2 कहाँ पे?
ओमेगा में तो नहीं.
Yes, ओमेगा में है. तो yeah, fine. ये जो ओमेगा है, it's not. We don't know that it's the mega of the oscillator. तो यहाँ पे मेरे पास आ रहा है h bar mega over 2, which is fine. It's just that in terms of this frequency, it's giving me h bar omega.
तो वहाँ 2h बार में कहा है.
2h bar omega. क्यों?
वो 2 आप कॉमन लेंगे ना सर.
2 कॉमन लूंगा बाहर. हाँ या तो मैंने क्या कहा था 2 मेगा is the cyclotron frequency. Let's give it a name, omega c. So now it's fine. h bar omega c a dagger a plus half. So in terms of cyclotron frequency, you are taking the jumps in this oscillator. So what's the conclusion? The conclusion is that this system has a spectrum of an oscillator. You can build up states starting from the vacuum. The lowest energy state in your system is obviously having an energy of half h power omega c, and then you can apply daggers to get higher and higher states, and you take jumps in h power omega c. The reason is that the classical motion is periodic with a frequency of omega c. So whenever you have periodic motion classically, quantum mechanically, you do get a harmonic oscillator system, which is where the energies are quantized in h bar omega. So these levels, classically आप रखता आप इसको किसी भी frequency सेम है, classically आप इसको किसी भी energy के साथ घुमा सकते थे. Bigger radius had more energy. Now that thing is just quantized, and you have these levels. Going up. These are called the Landau levels. कि जब आप किसी two-dimensional system में magnetic field को orthogonally apply करें, this system has these levels called Landau levels. और ये separation जो है is governed by how much field you have. More field, more separation, because it's related to the cyclotron frequency.
जितनी ज़्यादा रेडियस होगा हमारे इस सर्कुलर मोशन का, उतनी ज़्यादा एनर्जी होगी क्वांटम
नहीं, quantum mechanically you don't talk about radii. You just have wave functions. There's no paths, no nothing. Only in some classical approximation.
We cannot draw analog between the classical picture and the...
Well, you should never try to draw paths of quantum particles unless the wave function is giving you probability density which looks like a path. In general, there is no reason to expect it.
So sir, in this case, which electrons would go to the other side, would be able to cross?
अभी यहाँ तक तो पहुँचेंगे, अभी तो मैंने सिर्फ spectrum डेवलप किया है. If you want to know what the electrons are doing, the first thing to do, physically doing, where you will find them, first thing to do is to get the wave function. But these levels are there. लेकिन we are missing a one complete degree of freedom. क्योंकि ये क्या है मेरे पास एक oscillator है. Over here सिर्फ एक A dagger का pair है, so it means it's a one-dimensional oscillator. इसका wave function मैं लिखूंगा, it will depend on one coordinate. But my system is two-dimensional, so wave function has to depend on two coordinates. So I'm missing a whole coordinate. उसकी वजह ये है कि यहाँ पे I was playing with two operators only. So there is a huge whole degree of freedom still left, which I can explore. So consider this combination. हमने इन दोनों को ऐड किया था और इन दोनों को सब्ट्रैक्ट किया था, and we found that they are canonical, almost canonical with a constant. So what if I flip them? Flip the signs. Obviously it will give me an independent operator, independent than this. So I'm looking at something like this now. Sign change करके ये operators आपको क्या देंगे? तो what matters is the relative sign. इसमें से मुझे m omega जो है बाहर common में ले लेता हूँ. So let me rather write it like this. ठीक है? m omega मैंने common ले लिया. And minus से multiply कर दिया. वहाँ एक overall constant है. I don't care about overall constant. Just define it like this. वजह ये है कि those guys they look like momenta. Momenta को shift किया. these guys look like positions, but not just positions, उनको कुछ shift किए. तो दूसरा जो है ऐसे होगा, again flipping the sign over there, and now you can check. ये अपने पास क्या है? Showing it.
minus 2i is
ये जीरो हो गए, ये जीरो हो गए, इसने आपको दिया I over m omega माइनस I over m omega, क्योंकि मैंने इसका बना माइनस I over m omega, इसने भी दिया माइनस I over m omega, so you get ठीक है, ये सब तो नजर आ गया, ये कम्यूटेटर, ये जीरो, ये और ये आयोटा इस पावर दिया माइनस ओवर m ओमेगा, फिर ये और ये इसमें भी आपको वही टर्म दी, so it becomes 2 times. Now I can, but these operators, they don't enter the Hamiltonian. ठीक है? This is important point. I can define these guys, and this is now just for fun, for now, because it's not going to reveal anything about the spectrum. These operators, they don't enter the Hamiltonian. Hamiltonian doesn't care about it.
Sir, but like you can always जैसे पहले हमने क्या you wrote out the Hamiltonian in terms of pi and phi, you can always backsolve and plug them in. Then px to you write that as step 2y minus small y times n omega. Plug that in, we are having.
You can do that, but what will turn out then is कि जो Hamiltonian है, नहीं कैसे होगा? Everything will cancel, I guess. You will have x hat and y hat. ये px है, you're saying कि इसको मैं solve करूँ in terms of y hat and y, x and hat and x. मेरे पास ये है, I'll get something in terms of x square, y square. Well, yes, and then I'll have my Hamiltonian only in terms of x hat and y hat, but then it will not depend on px and py. Then I should only consider this oscillator in the Hamiltonian. So आपकी choice है, you can do double counting. या तो ये ले लें, these pi's, या ये ले लें, x and y hat. In the end, you have an oscillator over there. इसकी terms में लिखने, उसकी terms में लिखने फर्क नहीं पड़ता, because both are oscillators, but only one of them. When you are putting it back, तब आप एक को eliminate करके दूसरे को ला रहे हैं. So let's make these omega again something like जो पहले किया था. The important point why they don't matter to the Hamiltonian is this. if you take these B hat and B dagger, you can compute this. This is almost obvious. This gives you equal to 1. वही जो calculation वहाँ थी, you can go through it again. But if you compute this, all these, they are zero. So what's happening is, so suppose you start with, you consider just a one-dimensional system. Then X and P give you a complete set of observables. In the terms में you can write your all the wave functions and stuff. If you know what X does to your wave function and what P does, you know what everything else does, because everything else is made up of X and P. If you have a two-dimensional system, you have to know what X, Y, Px and Py do to your states. That's what you want to know. यहाँ पे we got some states, eigenstates of the Hamiltonian, and we know, let's first write them like this, the Landau states. X and P को मैंने replace कर दिया था A and A dagger. It's not, I don't just have a vacuum, I have all of these Landau states. I know what A and A dagger do on this. Okay? So half set का मुझे पता है. I'm missing half of the coordinates. That's the point. Half of the operators I was missing, which I have found now. Z and Y hat. And why I chose this particular operators? Because they have this nice commutation relation. Now I know what they do. They don't disturb what A dagger is going to do.
So what you're doing now is constructing the complete set of commuting operators and you
Not commuting operators. I'm telling, no,
you're going to remove the degeneracy.
yeah, that's what I'm doing. So what I'm saying is, both things are happening. एक तो ये कि I should know पूरे जो set of operators हैं, उनका action क्या है मेरे states में, ठीक है? So in other words, as I said, I only had kind of one coordinate. With the help of the other is also inserted. अगर आपके पास two-dimensional system है and the wave function is depending on x and y, you know everything about the wave function because you know how the position operator acts, how the momentum operator acts. Momentum in x and momentum in y. I didn't have that thing over here. I had only one coordinate, not x, some mixture. Just one coordinate. I needed another one. That I have brought in through this construction. Because now I have these four independent operators जिनका मुझे action पता है. And actually you can disentangle these guys and find what your canonical guys do to you. Because all of these are written in terms of canonical. And they are independent in the sense, linearly independent, in the sense that you can solve the canonical ones in terms of these.
This is one more thing, like you began with a set of Landau operators, now you have another set of
Another set of pressure operators.
How was the degeneracy visible in the Landau states that kind of motivated you with this? How do you see
So
that?
I was coming to this point. What he's saying is this thing. कि classically हमारे पास ये था कि एक तो इनके sizes थे. That corresponded to different energies. And that over here was what is the n in the Landau levels, because that's how you change the energy. But classically, you could put any energy state anywhere on the strip, and the strip is kind of infinite, too big. So if you can put them anywhere, you have a huge degeneracy, in classically speaking, over here. What is the analog of that in quantum case? That, as I said, was apparent over here. That the eigenstate depends only on one coordinate. The other coordinate, you can keep it free. You can kind of multiply the other coordinate, any arbitrary function. It will still be a solution. It will still be an eigenfunction. So there's this huge degeneracy. उसको सिर्फ मैं quantify कर रहा हूँ using these new set of ladder operators. So using these ladder operators, I can write my Landau states like these. Now you have complete freedom, the complete description of your state. And what happens is a dagger changes it to 1 plus 1. Because this set also exists. So I can have it act on my Hilbert space. My complete Hilbert space starts from here. Both of them can act. This raises this one by 1. This raises this one by 1. But energy does not depend on M. Energy of any of these Landau levels is it just depends on N, does not depend on.
Given that you've written out H in terms of A and A dagger,
A and A.
but if you write it out in terms of
B and B dagger, then A and A dagger will be freely hanging. So then the others will not do anything to anything. So they are just two sets of oscillators, A and B. In the Hamiltonian, only one set will go. Doesn't matter which one you call A, which one you call B.
So how did you decide capital X and capital Y? The two statements that you wrote, they are not equivalent basically, the Y
कौन सी?
this Y max.
What do you mean not equivalent?
Like there is a factor minus 1 over m omega, which is different.
ये?
Yeah.
Oh, I just said कि मुझे जो वो operators हैं pi,
Yeah.
उससे मुझे sign difference डालना है to
Okay.
make them independent, linearly independent, right?
Okay.
तो मैंने sign difference डाला, बाद में overall factor जो भी डालते हैं doesn't matter. So I took minus m omega outside and then forgot about it, divided by that.
So in the end, you guessed it.
Yeah. Well, you can keep it hanging. You can keep it hanging. Won't do anything to this thing.
so the idea
आपको सिर्फ एक सेकंड, आपको सिर्फ यहाँ पे स्केलिंग डिफरेंट करनी पड़ेगी.
so you wanted to construct linearly independent operators which would satisfy the economical commutation equation.
Yeah.
That's what you want. And the only way of doing that is sort of exchange the
Yeah.
sanctions.
Question? So if I have like a two-dimensional oscillator with x and y, so the difference between this system and that system basically comes at the level of degeneracy. In that case, there's no degeneracy, whereas here it is.
Yeah, the difference is coming because of the Hamiltonian. If you have two-dimensional oscillators, and if you have same spin constant in both directions, then this is your Hamiltonian. In this case, there's no this term. There's only one oscillator, the other spin is broken.
So
It's
sir,
degenerate, completely degenerate.
सर पोजीशन x जो होगा हमारा सर वो डिपेंड
You,
होगा
आप इसको ऐसे भी सोच सकते हैं. अगर मैं इसको ऐसे कर लूँ, दोनों स्प्रिंग कॉन्स्टेंट डिफरेंट हैं. ये frequency 0 है, there's no spin. So ये यहाँ पे नहीं आएगा. But the states I can still build. I can take omega going to 0. So states look like discrete, but there's no energy associated with them, so that discreteness doesn't mean much.
It's broken to degeneracy.
Yeah. So what you have here is that the Landau levels are infinitely degenerate. Either way levels बनाए हैं. That's not really true. Each level has infinite spaces.
Sir,
But that's not really true because I'm kind of assuming that the strip is infinite in size. We will right now see that when we have a finite extent of the strip, this degeneracy is finite. G.
सर इसका मतलब जो x है हमारी वो डिपेंड कर रहा है n और m पे in one sense.
X कौन सा?
सर जो इसको पोजीशन कह सकते हैं सर.
Position क्या operator?
सर पोजीशन ऑपरेटर
What do you mean position operator?
सर
N and M तो wave function के indices हैं. It locates what is the wave function. ये operator थोड़ी है. So now let's see के wave functions क्या है. If you want to see के what the electron is actually doing, we have to have some idea about the wave function. So in essence, the wave functions you kind of know because they are just the harmonic oscillator wave functions. अगर आपने ये जो pi x और pi y लिए हैं, you're thinking of this guy as momentum and this guy as position, then you can write the wave function in terms of pi y. वो जो आपके होते हैं, something. Now this is not an operator, just a variable. ऐसे और यहाँ पे आपके हैं बाइट polynomials. ऐसे होंगे और इनके साथ you can still multiply another variable like one of those guys. Let's say f of x. Not a operator. So two variables होंगे. ये oscillator wave functions है और ये बिल्कुल hanging, freely hanging है. You can choose it to be anything. Doesn't really matter. But I want to write the wave functions in terms of the actual coordinates. कि उन coordinates में क्या है? So that I can predict like probabilities. तो ये हमारे polynomial और इस किस्म के wave functions होंगे in some coordinate. And I want to kind of see what is that coordinate. वो कौन सा combination है x and y का? क्योंकि ये जो हमारे polynomial है, it's just a function of one coordinate. What is the combination of x and y which goes in there? That's I'm after. Okay? Because I have the wave function in the end in the coordinate representation is a function of x and y. I know it's going to split into one variable going in here and another variable going in here and another variable going in here. ये दोनों variables same है. क्या ये x है? Obviously it can be x. It cannot be y because that won't solve it. इसमें तो px और y Hamiltonian में mix up हुए हैं. Can't be x or y. Has to be a combination which goes in over here. And I want to see what is that combination. और in simple words, I just want to write the position space wave function in terms of ordinary positions, actual positions.
Combination part to elaborate that.
क्योंकि मुझे ये पता है कि मेरे पास वन डायमेंशनल ऑसिलेटर है, तो किसी बेसिस में आई कैन राइट इट, बल्कि इसमें अगर मैं देखूं, ये मेरा मोमेंटम था, ये मेरी पोजीशंस थी, ठीक है? अगर मैं इसका बेसिस बनाऊं, पोजीशन बेसिस, इसको वेरिएबल लूं एज अ पोजीशन वेरिएबल, इसको लूं माइनस आई इज बाय d by d by y, I can write my Hamiltonian polynomials. ठीक है? But I'm saying I can always write my wave functions in the actual position basis, actual positions, x and y. It may look like something like this, but cannot be x or y. Only one thing has to go in here, but it cannot be x or y. It's something else which represents py, pi y. What is the coordinate which represents pi y?
So in other words, you want to sort of know the matrix element.
Yeah, in the position basis. Yeah, that's another way to say it. इसके position basis में क्या representation? State. ये क्या है? So that we're going to do using kind of a trick. So we have, let's go to a new board. I have this thing, pi x hat plus iota h y. All I need to do is write this. यह ऑपरेटर मुझे पता है कि ये है क्या, pi x की वैल्यू भी मुझे एक्सप्रेशंस पता है. I'm going to write these operators in position basis. Once I write them in position basis, I know I have to solve for this wave function. Because the ground state, whatever it depends on, is annihilated by A. Excuse me? Question?
And it's a confusion thing clear over.
That's it. So, the position space, the wave function is going to be, the ground state wave function is going to be annihilated by A. Okay? And if I write this in position basis, ये भी position basis में होगा, then I will solve the differential equation. So just write it in position basis. क्या आएगा? ये जो है pi of x, it was just the momentum shifted by the position. कहाँ पे लिखा है? जहाँ पे हमने मैकेनिकल मोमेंटम की वो लिखी थी. हाँ? ये हाँ ये लिखा px plus m omega y hat. So px की in position basis is just this, y hat is just y. So I get and plus I and then I have P y है, pi y है, pi y is Py. I gives me a minus, 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 plus, and minus I m omega x. Minus m omega x वहाँ से, I यहाँ से है. d by dx and h bar मैंने यहाँ से कॉमन ले लिया और माइनस I भी कॉमन ले लिया, so I get plus I d by dy, because when this will go in it will make it a plus, or x plus Iy. ये ऑपरेटर है. अब ये जो ऑपरेटर है जिन्होंने थोड़ी बहुत कभी टू डायमेंशनल फील्ड के लिए या सुपरसिमेट्री ऐसा कुछ किया हुआ, यू नो हाउ टू हैंडल दिस. इसको कैसे करेंगे आपको तो बताइए.
Partial Z, वो complex way.
So the best way to deal with these guys, क्योंकि this looks like a z, the complex variable, and this is also a derivative with respect to complex variable directly dz. कोई बीच में आपस में कोई वो नहीं है, स्केलिंग्स नहीं है. स्केलिंग्स हो वो भी आप रिमूव कर सकते हैं.
But so we have to, I mean, this one like,
Huh?
I mean, you get a new integration measure for this, right?
But I'm not integrating anything. I'm just
Yeah, I mean,
I'm writing a differential equation
yeah.
and solving that differential equation. Or integration measure कोई आ भी जाए तो what's wrong with that? Okay. So this is a differential equation in the end. उसको सिर्फ मैं easy करके लिख रहा हूँ. And why it works? So define these complex variables. ठीक है, तो अब मेरे पास दो रियल वेरिएबल है x एंड y. तो दोनों को मैंने पैकेज कर दिया z में. Z bar gives the other combination. So z and z bar becomes two independent variables. If you know z and z bar dependence, you can disentangle and find the x and y dependence. Specifying z and z bar is as good as specifying x and y. क्योंकि इन दोनों को मैं सम करके x निकाल सकता हूँ और y निकाल सकता हूँ. This guy, ये क्या होगा? d by dx, क्या आगे डालूं?
Partial x by partial z.
हाँ, नहीं d by dz है तो d by dx आगे
dx by dt.
dx by dz.
you put a minus in here. It will be nicer if you put minus. तो इसको define करो, इस derivative को, इस operator को. So I can do it half the, it will make it more nice. That's why it's there. The d by dz को sometimes people just write del, and इसको sometimes people just write del bar. इसको मैंने माइनस से क्यों किया? इसकी वजह ये है कि if I do this dz bar, let's first do dz over dz, क्या आपके पास आएगा? इसने इसको डेरिवेट किया, gave you a half. जब इसको करेगा पार्शियल है 0, ये इसको करेगा 0, ये इसको करेगा तो क्या देगा? यहाँ से 1 हाफ, आयोटा माइनस, ये इस माइनस से मिलके प्लस हाफ हो जाएगा. That was the point. So this gives you 1. अगर मैं माइनस ना डालता तो उसमें मैं 0 देना था. While this guy ये बात देख ले, ये 1 हाफ दिया, इसने आपको आयोटा माइनस minus minus plus overall minus. So the both things cancel. This gives you 0. तो इस वेरिएबल का ये फायदा है इस तरह से पार्शियल डिफाइन करने का कि ये अब जो पार्शियल डेरिवेटिव्स हैं they have become independent. They treat this z and z bar as independent variable. क्योंकि partial of this guy with respect to this is 0. Just like between x and y or x and t or y or z. Similarly, and dz bar over dz bar is 1. So now you can forget about if z and z bar are complex or not. They are just symbols. And you have their partial derivatives, which are just like any derivatives of two independent variables. So now you can write this thing in terms of z and z bar. This will greatly simplify. And z and z bar are just two symbols. You can now solve your differential equation. And in the end, if you want, you can come back to your original variables.
जी.
So जैसे हाँ बस initially जो x और y थे अब हमने उनकी substitute कर दिया 0 0 वाले. What difference basically?
It simplifies things. तो अब ये इक्वेशन जो है in terms of these ये क्या बन गई है? A has become ये क्या? D by dz bar और ये है 2 times z. तो इसको मैं थोड़ा सा और इनको बाहर ले देता हूँ, 2 को कैंसिल कर देता हूँ. I get minus I h bar m omega h bar d by dz bar. इधर क्या आ गया? m omega over 2h bar. माइनस आयोटा बार ले गया ना तो प्लस हो गया. इसके सामने माइनस आयोटा था. हाँ ठीक है. Now this is the operator and it's acting on my ground state जिसको अभी मैं in new variables की terms में लिखा हूँ. It has to annihilate it. So if it annihilates it, z bar omega over 2h bar ये डिफरेंशियल इक्वेशन है, बाहर वो कांस्टेंट्स तो जाके जीरो हो जाएंगे। दो वेरिएबल्स में डिफरेंशियल इक्वेशन है, मगर इसका सॉल्यूशन लिखना इज वेरी वेरी इजी। वो कैसे? वो इस तरह से कि बिकॉज इट्स टेलिंग मी व्हाट टू डू। dz बार से मैंने डिफरेंशिएट करके एक z नीचे उतारना, तो ये दोनों कैंसिल हो गए। सो इफ आई ट्राई दिस, e minus alpha, I can put a plus as well, doesn't matter, खुद ही fix हो जाएगा, मगर let's put it like this. So d by dz bar of psi naught brings down minus alpha z. तो अब इसको अगर मैं ऊपर डालूं, the two things will cancel if omega m omega over 2h is equal to alpha. So that means my wave function is, this is the ground state. ZZ bar और ओमेगा वो क्या था, 2 times ओमेगा c, और ओमेगा c was 2 times ओमेगा। हाँ, तो यहाँ पे मेरे पास h bar ZZ bar आ गया, और ZZ bar क्या है? x square plus y square. So the ground state, it depends only on r, the radial. So these are rotationally invariant thing. It's a Gaussian in r. ऑसिलेटर के ग्राउंड स्टेट में वहाँ पे 4 होता है, 2 होता है, 2 होता है। You have to absorb it in some rescaling, 2, or maybe we just missed along the way somewhere.
Normalization is sort of common.
Normalization, इसको normalize करना है इसमें क्या?
Will it continue to depend just on R when you have higher states?
Well, higher state देख लेते हैं हम, if we have some time. या नहीं है?
क्लास स्टार्ट होगा, ये तो
अच्छा चलें, ओके बल्कि चलो वो I had a lot of comments to make, next time करते हैं। सिर्फ मैं एक बात, ये उन्होंने क्वेश्चन पूछा उस पे कमेंट कर दूँ, फिर आगे इसके आगे नेक्स्ट टाइम देखेंगे क्या इसका होगा। तो अगर मैंने दूसरे बाकी स्टेट्स देखनी है, दिस इज जस्ट द लोएस्ट Landau लेवल, ठीक है? बाय द वे, व्हाट अबाउट द अदर डिपेंडेंस? अभी भी एक कोऑर्डिनेट पे करा, मैंने कहा था मैं इसको एक और फुल रेंज ऑफ कोऑर्डिनेट है जिससे मल्टीप्लाई कर सकता हूँ, वो कौन सा है? If I take this function and multiply it by any function of z, because when I was solving this, I didn't put any free constant in my there. There's a free constant. It's a one-dimensional equation. You get a free constant, but that is a constant which depends on z. Why? Because in my equation there's no derivative with respect to z. This f of z will just go through. So I can take that and multiply it with any z function of z, it will still be my ground state. So that's telling to you the degeneracy of the lowest Landau level. All kinds of wave functions, as long as they depend on radial coordinate this way, you can multiply with this, they will still be living in the lowest Landau level still the eigenfunctions of the Hamiltonian. So जो next का पूछ रहे हैं आप, we will see it next time. Wave function तो नहीं करेगा लेकिन probability densities they will only depend on radial.
I'm just going to be on the same point. I mean, like, if it's what's the resolution of the identity in terms of the dot. I mentioned it for the same reason I was talking about normalization, for the same reason I was talking about, because I think that's right.
Resolution of identity.
For normalization.
You mean how to integrate? That's not resolution of identity. That's integration.
I mean, what's the measure? Because you're shifting the
This
yeah.
is dz bar. Just check it. There's a factor of 1 by 4 or something. ये z length dx का dy by
What is the usual behavior that
yeah.